I'm Aedan Cullen. I'm currently a college student. I study computer science. I also do a lot of electronics work in essentially all my free time. And today I'll be talking about a particular project I've been working on for the past few years, where I've been trying to get as far as possible along the road of building a practical augmented reality device. So I'll go through, telling the story of this journey and a few of the things I've learned along the way. So this story really starts quite a few years ago. I did a project around the 2014-15 timeframe where I wrote some software for an AR system and realized that AR software is quite easy. This was a project I actually did in middle school where I developed a network protocol. The idea here was, what if you had a device that looked like a normal pair of glasses but could display information overlaid on the world? How would you use this in a practical way? How would you set it up so that it was useful for you? And I thought, well, you would deliver content to it from, sort of edge computing resources, Wi-Fi networks, nodes that you can connect to as the user moves around the world, and deliver the data in that sort of way. Make the data contextual, give the user information related to an IoT device near them or something related to what they're doing in the world. So you could have virtual signs that appear in the world, interfaces that are displayed on certain surfaces. So for example, the weather showing up near the window or something like that. So this is a view of what I call lightweight augmented reality. The industry is really going to have to come up with some terms for defining what these AR devices do. In my view, this lightweight AR concept is just the idea that we don't need to have some wearable device that provides a completely immersive, 3D, visualization. That's not really necessary for us to get some good practical applications out of this. All we need is physically relevant information and physically intuitive interfaces for the users. And from those motivations, you start to think about what the hardware should look like. It should probably take advantage of edge computing resources. So this is the idea of having servers closer to the device than the cloud. But then you can do some work with offloading computation to those edge servers. There's been some interesting research in that. And another thing you realize is that a lightweight AR device probably does not need two displays. Even if you had a high quality, high resolution display in one eye, you could still achieve these physically relevant and intuitive interfaces that I was imagining. So around 2019, I started thinking about actually building this hardware, what you would need to accomplish for it to be practical. These are the considerations which would cause someone to, decide it's not any good, right? So if the display resolution is not up to par, then they're going to choose to use their phone, essentially, instead. In my view, you're essentially competing with phones in designing these sorts of devices. So the angular resolution, pixels per degree would be one way to measure it, needs to be comparable. The field of view should also be comparable to a phone you would be holding in your hand. And from that, you can gauge that the overall display resolution should at least not be orders of magnitude different from what you have in a phone. And software and hardware needs to be very reactive and responsive in an application like this. You can't have the user turning their head or making some interaction with their hand in the world, and you can't be slow to sense that. You need to be very responsive in sensing that and reacting to the user input. So in some regards, this is a whole new frontier in terms of user interface design. And then you have the typical mass volume, battery life, and power consumption considerations, which, as we'll see, are some huge design challenges. So this is a board which was actually the first PCB I ever designed with a BGA package, which was also the first board I designed with surface mount devices. So this was a simple test of a system-in-package device from my friends at Octavo Systems. So this is called OSD32MP1, and it has the STM32MP1 from ST Microelectronics. So I designed this board just as an idea of, okay, what might you put, in a glasses frame beside someone's head what sort of electronics could you fit in this system in package sort of architecture. So this didn't have a display yet, but it was my first venture into prototyping some small boards with BGAs and using system in package. And then we move on to display technology, because that's the thing this lacked. Now, around the summer of 2020, some information started to become a bit more easily accessible about these Sony OLED on silicon micro displays. So these are not the cutting edge necessarily of display technology, but they are a mature display technology now that you can use for augmented reality. They're essentially, a single silicon backplane with an OLED display on it. So this particular one is ECX337A. I designed a board to test it. I didn't use someone else's breakout board. I just went straight to designing my own. So it essentially has a parallel interface, a parallel RGB to LVDS bridge chip, and then the display attached. So I wanted to test this with that STM32MP1, for which I had a development board, of course, but they don't expose the parallel LCD interface. Instead, they feed it to a chip, which is an HDMI encoder. So, I don't want the HDMI encoder, so I just remove the HDMI encoder. And then you solder up your wires to get your parallel LCD interface. So this is what I do when I want something to work now, and I don't like how the evaluation board is designed. So then, my little test board with the bridge chip stacks on top, and the display works. So this was quite a nice accomplishment, I felt, because I hadn't found any other reference designs for this display. So that board design is on my GitHub page, and around this time, this tweet popped up. This display, by the way, is 1/2 inch diagonal, 1280 by 960 resolution. So I'm like, oh, the rumors going around are that companies are using these same sorts of displays. I don't know if these rumors are true or not, but it was cool to feel like I was at the front of this, sort of cutting edge display technology that is kind of an emerging thing. Not many makers know about it. So then I put essentially that development platform onto a smaller board with that system in package. So that's here. And then this I actually, assembled, and you can connect the display to it like that. So then this is the design that I did put into a complete wearable device. First I have just a block diagram of it, essentially showing the LVDS transceiver, display, system in package with the DRAM integrated, and then a bunch of sensors, IMU, power supply stuff, and so on. So this is what it looks like turned on. As you can see, there were a few bodge wires, but that's to be expected with the first run of something like this. So here, before I show the complete assembly, this is kind of an overview of a very simple optical setup that I decided to try. So of course you need to get the image from the OLED display to the user's eye, and about the simplest thing you can do is use a converging lens, in this case a double convex lens, and a beam splitter. So then it's assembled like this with the board vertical in this kind of unfortunately large enclosure at that point, and the battery was placed beside the board like that. And so this is what it looks like straight up and down. So the goal with this is just to see, how compact can I make this optical system? And of course, if you wanted to have traditional glasses lenses, you could design the system like that as well. And you can take decent enough pictures through the optics. I was happy that this worked well enough, and I was satisfied that I could design at least a decent optical system from scratch without using an off-the-shelf module. So from that point, I moved into how do we improve this? Now, one thing about that STM32MP1 microprocessor is it's not terribly power efficient. If you run the display and just have Linux sitting at idle on that system, you're typically looking at over 1 watt, just with Linux idle, like display on and everything like that. So, you have to try to go into low power modes. STM32MP1 does have a Cortex M4 coprocessor, so there are some interesting things you can do with that. But in general, I needed to look for ways to take advantage of low power architectures, ways to eliminate extra components like external bridge chips that consume more power converting between display interfaces. And of course, as I learned from the start, integration of components is going to be very important. I would guess that in the future, it's going to become wisdom in the design of these devices that you have to have system in package, essentially. If you have, traces on your PCB for DRAM interfaces, that's probably a waste that you could put in a more compact package. So there's this kind of hierarchy. This is kind of how I see these challenges. One very problematic area, in my view, is software. What sort of user interface can you provide per unit of performance? If you have very inefficient, bloated, and slow software, then the user experience is not going to be great. In the design of these devices, significant advantages, I think, can come from more efficient and effective software. And part of that also is networking and offloading compute to edge devices. So in other words, you care about user experience per gram. You want to make these devices really tiny, really light. So this is another iteration of my design. Now here I've switched to a different system on chip. As you can see in the assembled view, this is using this package. It's marked F133. It's also called the Allwinner D1, which is known as one of these new RISC-V system on chips. This is made on a 22 nanometer planar process, so it's relatively efficient in comparison to the older 40 nanometer STM32MP1. So this chip also has a dual link LVDS interface built in. So you don't need any sort of display interface bridging. It has the same sorts of peripherals. A few things have been added. Same IMU microphone, Wi-Fi. Now I have a 2-channel biopotential front end, and the idea of that is potentially doing eye blink detection using electromyography. So there are a lot of interesting things that can be done there. And here are some graphics of how I imagined putting this in an enclosure. So essentially, I'm envisioning here a sort of brim design which sits over the top edge of a glasses frame. So rather than having the board vertical on the side, I said, well, what if you put the board horizontal, sort of in front of the user's eyebrow? And if you continue making your board narrower and narrower over time, then you could make this look quite compact. So the display sits next to it like that. It ends up stacking into this relatively neat and tidy little arrangement with the display flex cable folded like that. And there are some 3D printed parts that sit on the top to hold it together in this overall enclosure. So then the enclosure is less than 10 millimeters high. So it ends up being pretty flat when you look at it from the side. So that was the motivation for this mechanical design, was to make it kind of narrow when you look at it from the side, and then work on squeezing the width of the brim down. So here are some interesting renders of this design. And in these images, the optical system here, I've actually rendered a freeform reflector for which you can compute the optimal surface shape, and this would remove the requirement to have a more complex system of converging elements and a beam splitter by just having a single element partially reflective with the proper curvature to both to put the display in focus and bend the optical path. So there's also code for that on my GitHub. I don't really have time to talk about that, but I went through quite a few iterations in developing this mechanical arrangement that you see here. And then, yeah, so this is the finished product. There's kind of a collection of all of the various electronic components that I've designed as part of this project. And essentially, my motivation with this in the future is to keep trying to push in the direction of lowering the electronics power consumption, increasing the display resolution, and relying on compute offload to edge nodes or a phone in your pocket, and efficient software design to get that sort of user experience that I'm looking for, with lightweight information displayed in relevant places in a pretty inexpensive device. So here are some general overview of where I'm currently at the moment. So this prototype was mostly designed in 2021. Its display resolution is significantly higher than quite a few of the competing devices with a similar sort of design goal, I would say, in terms of their appearance and trying to be slim and sleek. What I'm doing here essentially is putting more effort into display technology and less effort into compute. So both Vuzix devices and the Google Glasses devices are essentially an Android smartphone stuffed into a pair of glasses, which in my opinion is not a very productive way to go about this, because when I was designing with a very power hungry processor, the STM32MP1, you become very frustrated quickly with power consumption issues, and that's how I became motivated to go in this sort of efficient computing direction, where I really want to reduce the compute on board and just focus on user interface stuff. So the mass of this is about 42 grams. I always want to keep the mass of these devices below 50 grams, because that's kind of the threshold where I feel like it becomes a bit excessive compared to a pair of sunglasses or ordinary glasses. And I'm currently working on a design that I've been doing this year with a full HD 1080p micro display. So some more information might show up on about if I have a reference design for the display I'm using here, I might publish that. And I still want to keep this around the same price point of under $500 and less than 50 grams. So overall, the things learned from this project, I would say, are that it is certainly possible to do this kind of what I would call cutting edge electronics prototyping, in the sense that, that Sony display, when I first started designing with it, I needed to sign a non-disclosure agreement to get the datasheet. And you quickly become accustomed to this quite troublesome, in some sense, process of contacting manufacturers to get data sheets and explaining why you want to use their parts. And getting familiar with that process has been one of the most interesting parts of this experience, I would say. But I was trying to kind of prove to myself that I could work with this new technology and make progress with it. So this design that I'm currently working on goes a bit farther with the electronics miniaturization. So it's going to have a high density interconnect PCB with the laser drilled micro vias, via and pad, and all of that fun stuff. These designs I've done so far have really been getting to the very limit of what you can do with plated through hole and traditional mechanical drills, without blind and buried vias, and you essentially just run out of space for vias. I didn't mention, but this is a 6-layer board, the one that I designed mostly in 2021, and the earlier prototype that I showed, those were 4-layer. So, some more information about display prototyping could show up on my GitHub. If I make any significant new progress with these prototypes, I will probably post about it on Twitter at Aedan Cullen. And if you would like to take a closer look at these devices, you can talk with me afterward. And yeah, I hope that if anybody else is thinking about, I should try this very hard electronics project that may just not even be useful, I would hope that something like this can encourage you to go ahead and try it, because I really cannot think of any possible project that would have taught me more than this one did. Now when I look at some electronics challenge, like, making an add-on for this badge, stuff like this seems, easy. Like, of course I can do that. Once you try something with so many problems and so many issues, like wearable electronics. So try hard projects. You'll make progress with them, even if you have to, navigate new areas of crazy display technology and things like that. So thanks everyone for coming to my talk. And if you have any questions, I can answer them.